Right, so I'm going to try to say today a little bit of what, remind people, most of you at least, what pseudoholomorphic curves are, say a little bit of what the moduli spaces are, and give a first hint of what regularization actually is. Mainly it's a word that I've introduced because I think there's more to things that need to be done than the slogan that we've used, which was transversality. So, but that means, of course, we start not with 1, 2, 3 things, but with just background to really set notation, make sure we're all on one page, and we have this all on a nice page here. So, so my symplectic manifolds are pretty much always. Hold on, I wanted to do this gray. Yes. Always going to be compact. They're automatically even dimensional, that's usually 2n, compact, and I'd like them to not have boundary. There are other cases that one could look at, but if I don't say anything, I'm going to assume them to be closed, smooth manifolds. And then this omega here is a symplectic form. So that's a 2 form on M, which is closed, and something called non-degenerate, which has various forms. One of them is that if we wedge it n times, we will get a volume form. So everywhere non-zero. Right? And that in particular means that our smooth manifolds are actually always oriented. Yes. If you see anybody at the door, holler. Okay, so if I write M omega, I mean symplectic manifold. If I write M, usually I mean with a distinguished symplectic structure. And the example that we spend a lot of time with in the non-squeezing proof was the example that we got from a potential squeezing map. So it was CP1 times some large torus. Total dimension here is 2n. And we had a variety of symplectic structures on this. Right? So we were going to take spheres of area slightly bigger than pi. So there's a standard omega volume form, actually. Let me call this a volume form here. Plus epsilon. Right, volume form on CP1 is closed 2 form. It's non-degenerate. And then on the torus is a quotient of R2n or of Cn, so on that we can write down the standard complex structure, which we get from wedging the real parts and the imaginary parts of our complex coordinates. So this would be on, what is that, Cn minus 1 mod C. 2n minus 2. Right, and the coordinates in Cn here are xl plus I yl. Which is the reason that that index isn't called I, but L. Okay, and well, right, you can also multiply this with some constants here. So, well, k should not be 0 here, otherwise that's not non-degenerate. Epsilon should not be -1. Right? So, in our case, we had both epsilon and k positive. All right. Good. So, that was the symplectic manifold we were looking at, and before we can say holomorphic curves, we need complex structures. Before we can say pseudoholomorphic curves, we need almost complex structures, and they're always going to be compatible with omega. So that means my J here is going to map a tangent bundle to itself, covering the identity on M. So it's going to be a linear map on each tangent space, squares to minus the identity, and it's compatible with omega in the sense that if I stick J into one factor of omega, I'm going to get a metric on my manifold, which is usually called G sub J. Okay, and well, the example, the nice example that we were able to really understand holomorphic curves in for this product manifold was what I had called J0, something that you get from I on CP1 and also I on Cn minus 1. So that's in fact a complex structure because it locally looks like I in Cn. Right? And important fact here that Shin nicely explained in the student seminar last semester is that this space is not only non-empty, it's also contractible. That means for algebraic topologists it's simply a point, and for us that means that the Chern classes are well defined and independent of the complex structure. So if you take the tangent bundle together with the almost complex structure J, that actually is a complex structure on this bundle, so that has Chern classes, which will be 2L homology classes. And they will be independent of J. Oh, goodness, yes, obviously. Thank you. All right. Good. So, well, really, we're only going to need the first Chern class at some point, but and it's just going to appear in an index formula. It's good to see that first result. That the space has, gives more structure on symplectic manifolds. Okay. So, before we can talk then about pseudoholomorphic curves, which give us a lot more structure to study on symplectic manifolds, we need to think about, well, the simplest example of pseudoholomorphic curves, namely just, well, curves in algebraic geometry, which for us are two-dimensional surfaces. So a Riemann surface for me is a surface that will be, well, an oriented two-manifold that, I'm not going to say closed here because, once we talk about Floer theory, those will be cylinders. So we might want to do pseudoholomorphic disks. So boundaries do appear here. In the examples, usually I won't have non-compactness or boundary. And J is one of these almost complex structures. Except it doesn't even need to be compatible on these Riemann surfaces. They're automatically complex, so locally these surfaces all look like a piece of the complex plane with the standard complex structure I. So that's Riemann surface, and the main example that we dealt with were spheres. So easiest way to think of them as a CP1 with J again I. So I guess that these all locally look like complex plane is already a fact there. It's the integrability. Okay. So with that, I can say what the Cauchy-Riemann operator is. Well, roughly speaking. So really, I should have all the data here, you know, M, J, little j, right? But usually, we just label it by the capital J, which is somehow the important choice that can get changed. So Cauchy-Riemann operator looks at maps from a Riemann surface to a symplectic manifold and makes something out of it. Right. 0, 1 forms on something. So these will be things I might not really want to go into. What it is the antilinear part of the differential. So du, right, maps the tangent space to sigma to the tangent space to M. On both of them, I have an almost complex structure. And so I can look at the part of the differential that is antilinear. And that is the one I get by a minus sign here, I believe. No, plus sign. Right. Because j squares to minus 1. Or differently put, if d bar is 0, back 0, right, is d bar u is 0, if and only if du is antilinear, so is j linear, du j is j du. Okay, and there is another fact. Let's see whether I can. This one I haven't tried. Oops. No, I can't scale this. This point, I think. Can I scale this? Well, we'll have to work on seating arrangement because we have actual counts here. So let me not. Yes, let me do this. A little bit more space on my page here. So the other fact is that locally, and that's important for the analysis, my d-bar operator looks like the d-bar operator that we know from single variable complex analysis. And now is the time when you really should call my bullshit, because those are sections of a tangent bundle, and that certainly is some kind of one form. So that is not true in this sense. What I really mean to say here is there's a 2 here, and then I would multiply that with ds, and then I believe that's no, that is the -1 minus j times the same thing, dsu plus j dtu, oops, dt.
Now you want a ds.
Ah, yes. Thank you. Right, so meaning d bar u is 0 if and only if dsu plus j dtu is 0 in local coordinates. Nice. So that helps us with the analysis. Good. Okay, so that was notation as it might be coming out of your ears if you've been around last semester. And now comes a little bit more language that wasn't so important before, and it's going to become pretty crucial in order to stay sane when we try to talk about moduli spaces. So it becomes very important to differentiate between pseudoholomorphic maps and pseudoholomorphic curves. So the pseudoholomorphic map is going to be a map where we have all the structure around that we fixed before. Mainly, so it's a map from the sigma to M, and I'm just going to keep track of my extra structures. And it's pseudoholomorphic if the Cauchy-Riemann operator is 0. So far, so good. And then the fact here is that once we have one pseudoholomorphic map, we usually have a whole lot more. So once I have one, I can reparameterize it with any automorphism of my domain. Right? So, well, these are, well, diffeomorphisms of the surface that fix the complex structure J, and there's a lot of them. Well, in many cases, for example, for the sphere, so the automorphisms of CP1 with I, it's a 6-dimensional non-compact group. That's the Möbius group, which we can identify with certain matrices via, via thinking of CP1 as C compactified, and then these are the rational maps, I guess, that are not totally trivial. So what is that? AD minus BC is not 0. that looks 8-dimensional, but I can, divide everything by one factor. So I could fix this determinant to be 1, so I have 6 dimensions. And it's non-compact. So you're not going to find just a single holomorphic sphere. You're going to usually find a non-compact, set at least 6 dimensions. So that means one ought to quotient out by that. And so the pseudoholomorphic curve that's associated to the map, we usually think of that as a quotient in a space of maps mod automorphisms. And just to be totally anal, right, it's really helpful to have the equivalence class around that to not get confused. But then, how do I say that this map is actually, this equivalence class of maps is pseudoholomorphic, right? I should say that no matter which representative I take, it's going to be holomorphic. So, contrast this a little bit with algebraic geometry. In algebraic geometry, a curve would usually be, a subvariety of M, right? So there, when we're saying curve, really we're thinking more of a subvariety of M, with that complex structure then, which in our case might be the image of the map. But what symplectic geometers like to do is we'd like to remember whether this is, say, multiply covered. So we'd like to remember how this curve gets parameterized. Well, up to reparameterizing it on sigma. So that's the slight difference there. All right. So, and I might make mistakes in the language, between maps and curves. I'm trying to be very careful with that. So, okay, so that's pseudoholomorphic curves, and that begins to explain the word moduli space, because we've modded by something, and I'll at some point give more of a list of sort of all the kind of moduli spaces that get looked at in symplectic geometry. For today, I just want to look at Gromov-Witten type things. So I'm going to fix a homology class now in the symplectic manifold. And then, well, there's a space of holomorphic maps that represents the class A, and that is J holomorphic. So those are actually my maps, and those that lie in the homology class. So push forward the fundamental class of sigma to A. So here clearly I should take a compact surface to make sense of this. Otherwise I should maybe talk about homotopy classes or relative homology, something similar. So this is the space of maps. On this space of maps I have the action of the automorphism group, So there's a moduli space that now of pseudoholomorphic curves, which is this quotient. So, and then what we often like to do is we like to compactify that moduli space. So, and that's what we're getting if to this quotient we add trees of bubbles as we've seen, or some of us have seen from the Gromov compactness proof. And I'll say more about this because that gives a lot of fun with regularization problems at some point. But the first level of regularization problems will be even before this. So you can defer this a little. So, right, so words here is, so this is the moduli space of maps. This here is the moduli space of curves. And once I've compactified, I would call it the compactified moduli space of curves. So, more precisely, you should say the Gromov compactified moduli space, because there's many ways of compactifying a metric space. So, let's see. So, in the example that we toiled with all of last semester, my base homology class was just the fundamental class of CP1 and the point in the torus. That was a particular nice class because it was excluding bubbling. And let's see. I'm going to do this trick again here. I'll just push things up. No, actually, let me copy this. Copy. New page. And paste. Good. And now we can get rid of a bunch of things here. So we're not going to need compactified moduli spaces here. Like to keep that notation up here. And this guy. So then I can give you the 1 minute summary of everything I proved last semester. So the big goal was to prove that symplectically one can't squeeze a ball into a cylinder if the ball has larger radius than the cylinder. And we did that by finding a holomorphic curve. So, well, more to the point, we found, a specific, almost complex structure and a curve in the moduli space for that complex structure. But we had some extra conditions, right? So the non-squeezing, right, had something to do with an embedding from some large ball into, well, a cylinder, but then a cylinder became our CP1 times the torus. And what we wanted was that, right, so J lives on this manifold here. We wanted the pullback of J1 to be the standard complex structure on the ball. I should not say J0, because J0 was an example here. I'm just going to say I on this Cn. And we wanted the curve to go through the image of the center point of this ball. So center point should be in the image of U, which makes sense even for curves, because we're just reparameterizing. So that means we don't quite get away with these moduli spaces. We need a little bit of a sprucing up of these moduli spaces. So and there are two options of how to do this here. Option one would be to just impose this as something called a point constraint. That's what we did. Option two, sort of going to be the more educated and more general approach. We're going to talk about this in the context of evaluation maps. So what just happened? We'll see what happens with my order of slides here. Okay, so well, actually, let's try that game again here. 4, beautiful. Oops. Copy. Paste. Oops. No. What is happening? Ah. Here. Endless joy. Okay. So, with a point constraint, so now I've lost my notation for the moduli space. will get better with that. So point constrained, the space of maps is going to get an extra condition from a point P0 in M. In this case, that would be the phi twiddle of 0. So those will be the maps that are right in the right homology class, J-holomorphic, and at a fixed point that I'll have to decide on a priori, hit that point. So C0 in my surface is fixed. I can do that, for example, for the spheres, because if the sphere goes through the point at some place, I can always reparameterize the sphere. So, for example, that was 0 in CP1. Now, however, I can't freely reparameterize these guys, right? So on this space now, I only have a limited group acting. So the moduli space then is the space of maps modulo the group that fixes this mark point. So these psi's need to fix the mark point. Might be a lot of language, there's so we have the mark point fixed, and then the psi's need to fix the fixed mark point. Okay. So this really was the modular space that we were looking at for the Gromov non-squeezing. If we wanted to do the same thing with evaluation maps, I would do something slightly different. So in general, I could, for the Gromov non-squeezing, I should add one mark point. I could add any integer number of mark points. So these are now not fixed mark points. These will be freely moving mark points. So these are pairs of a holomorphic map and a tuple of points in my surface. And usually there's going to be some constraint that I don't want any two of them to be the same. But let me not get there right now. So now the mark points are sort of extra data. So these Z are also called mark points. And now I have a different action on this space. So my moduli space of pseudoholomorphic curves with mark points will now be the quotient, again, by the automorphism group, but I am going to act also on the mark points. So while reparameterizing U, I'm going to move the mark points as Z inverse exactly because I wish to have a well-defined evaluation map from the moduli space. So overall evaluation map here should now take, well, a curve with marked points, and I would like to just evaluate the curve at those points, so let's see whether that makes sense. Let me just take a representative and evaluate at all the marked points. That's exactly where the psi is going to cancel out, so that's the reason the action goes this way. So I do have a map from this moduli space now to k copies of m. So now there are different ways of saying what we tried to prove for the Gromov non-squeezing. In this case of point constraints, we could just simply say that this moduli space is non-empty. With the evaluation map, it's a little bit more complicated, right? We would like to say that, well, this evaluation map here, right, so k is going to be 1, actually hits the point that I wanted to hit. So those are a bunch of examples of moduli spaces. And going a little bit towards regularization in this. So what all these moduli spaces will have in common is some analytic description, at least of the main part, before we talk about bubbling. So, and I'm not going to talk about point constraints right now. So with k marked points or not. So my moduli, well, my space of holomorphic maps is, in all examples that I can think of, the zero set of a Fredholm section. So there's some Banach bundle, and my d-bar operator, in some sense, is a Fredholm section. And wherever that's 0, those are exactly my pseudoholomorphic maps. And it's nice to keep track of the index. The index is, well, governed by the first term class of the tangent bundle paired with the homology class that we fixed. Then, well, if I'm adding a bunch of marked points, I have a whole lot of choices where those go. So marked points moving is 2k. And then the genus of my surface is playing some role here. So to add the Euler characteristic of the surface times half the dimension of my manifold. That's just the Riemann-Roch formula there. That does not necessarily bias something for the moduli space of pseudoholomorphic curves. Right? So because we want to quotient by a group, and we don't know, well, I mean, there's an index here, but we don't know that this cuts out, a nice space at all. So that's where transversality comes in. So if this d-bar operator is transverse to the zero section, well, then this cuts out a nice, smooth manifold of this dimension. But then we still want to quotient by the automorphism group, so we need a quotient theorem. So if that automorphism group acts freely and properly, so at least then do I get a nice moduli space. So then my moduli space is a D manifold where, so whenever I have a D in the picture, now D is the dimension that I get from the Fredholm index minus, dividing by the automorphism group. So, and whatever the formula is, usually not that important. I guess there's one test case that I always like to keep in mind to make sure that I have the right formula. So for CP1, let me get this right, the Euler characteristic is 2. So D is Chern class plus number of marked points plus 2n and then minus 6 from the Möbius group. So the way to remember or to check that this is the right thing is to think about the Gromov non-squeezing case, where, well, I need to know what the Chern classes are. So the Chern class on this, just on CP1, that's just going to be 2. So I'm going to get 4 here. So in the example A, so this is a 4 here. How should I say this? Right, let me think about the, let me actually add a marked point here, right? So I have a marked point plus 2, then I have 2n extra minus 6. So I actually get exactly 2n. So which is good, because that means, when I map my moduli space with the evaluation map to my manifold, I'm expecting a 2n-dimensional image. So that gives me a good chance to actually hit the point. So I should get exactly 2n here. So that is the one. Test case to make sure that all my factors were right. Okay. So there's a lot of language. So now comes a time when I need to say some fuzzy things that will be the goal to explain. So what happened here? Oh, these moved down. So when you have one of these moduli spaces flying around and you'd like to count it, or you'd like to prove that there are curves in it or something, You know, you ask some wise people and they will say something that might sound like some of these slogans here. One slogan would be that the compactified moduli space of holomorphic curves is always a D-manifold for generic J. And it's also unique up to cobordism. And they might mumble something about branched manifolds. If they say orbifolds, they might have something confused already. So that is one slogan that's sort of closest to what I tried to prove last semester. Another slogan is that, well, this compactified moduli space has a virtual fundamental class. And by that, they will explain to you that although the moduli space itself might not have a fundamental class. Sorry. Did I introduce this notation well? So this full evaluation map, of course, has evaluation at every point separately, right? So although it might not make sense to talk about the fundamental class of your moduli space, the notion of a virtual fundamental class is that its push forward under the evaluation map exists as a D homology class in the k copies of your target. And the claim would be that that is well defined and independent of J. So, well, there's one good reason really to sort of not try to define this fundamental class in itself. The nice thing is if we're trying to talk about the a homology class on this side, that right-hand side really doesn't depend on J. Recently there have been more attempts to actually define that fundamental class, which really I would like to stop calling virtual, because it really ought to be a fundamental class. But if we're going to do that, we'll have to say what it is a class in. So, with any luck, this possibly very singular moduli space for a given J actually has a homology. And so then I would like to make a class in its Dth homology. So one way of making some sense of this is to take this as a compact metric space, and that has a check homology, and one can make at least rational check homology classes. And the integer check homology is the wrong thing to try and deal with. According that is not even a homology theory in some sense of that. requirement. So
Is the ordering of the mark points also fixed?
there's no ordering. Oh, well, ordering, well, so I can't order them like on a sphere, right?
Well, like
so
my maps in the moduli, like the elements of this moduli space are like pairs, curves with the set of k points.
Yes, yes. The k points are ordered. Yes, yes. I'm not right because usually I want z1 to go through some hypersurface and z2 to go through something else, and not the other way around. Right. That is. Ooh, that is true.
Otherwise, the evaluation would go to the symmetric product.
Yeah,
right.
That's what I was questioning, whether it's going to go to the
yes.
product.
Yes. So, right. That is a good question, and that goes directly to what I was going to say next. I was going to try to sort of give the link of, the slogan link to sort of more algebraic geometry type questions. But clearly there's going to be something wrong here. So, the other thing that people like to do is they like to write integrals over these moduli spaces. So if that was a nice, smooth, compact manifold, and I had all my evaluation maps, I could pull classes back. And if this is of the right degree, I could integrate this over my moduli space. So then the question is, what is that integral? Well, and the claim is that that is the same thing as imposing point constraints. So, so I should first say here that I guess the sum over the degrees of the cohomology classes here better be D. Expected dimension of my moduli space, otherwise that integral does not make sense. So if we can make sense of all of this, then this should be the number of J holomorphic curves that go through cycles that are represented by the Poincare residuals of these homology classes. But from what you just said, right, so we have our mark points ordered, so actually, right, we're asking here, so the first mark point is coupled only with alpha 1, not with some of the others. So we're philosophically asking here the curves to go through these cycles in that order of the mark points. However, so now we're getting to quantum mechanic-like interpretation of what we're actually doing. So if you're very focused in your mind of the moduli space, the mark points actually being ordered, then you might think that you're asking these intersections to be ordered. But if you come more from the geometry, if you see a curve that goes through a number of cycles, you would call the point where your curve goes through the first cycle the first mark point, and so on. So I believe you're actually you're doing the right counting problem here without an order imposed. Because you're finding every such curve essentially once, with the ordering given simply by where it geometrically intersects. that is a different question. If we were on a disk, right? So this question might have come from disks. On disks, sometimes we'll ask the marked points to not just be ordered as tuple of marked points, but to also be ordered on the boundary of my disk. Right? And so then I'm really geometrically looking at something else. I'm looking at a disk that along the boundary goes through a number of cycles in this order. So if my marked points float around on a two-dimensional surface, there's no intrinsic geometric order.
But you also quotient out the automorphism.
Right. Yes. Yeah. Right. I'm not. Right. I'm right. I'm only asking curves that go through these cycles somewhere. I don't care. You know how the parameterization goes. So. So all of those are slogans.
Can I ask a question?
Yes.
Can you quickly comment on the relative trustworthiness of the slogans?
None of these is trustworthy. None of them actually make sense as is, I would say. You know, because all of them should just, I think all of them can be made rigorous, and to some extent that's my plan.
Well, the first one is just false.
Right.
The second one maybe you can make rigorous.
Yes. Well, I think the first one is also false because now, if you say for generic J, I'm going to tell you, well, which J's are generic?
Okay, the generic J's are empty, then sure, it's true.
Yeah, I think just in terms of language, none of these are precise enough to even decide whether they can be true or false. Let me give you some true statements. So, in this context, the little bit of regularization that I proved last semester and before at MIT, and there's plenty of lecture notes and, well, obviously not just by me. We're using a Sard-Smale method to make some kind of sense of the first type of slogan. And we only did this in this very specific example, right, where my symplectic manifold is this nice product of CP1 and a torus. In particular, it's a monotone symplectic manifold. And we had a very, very specific homology class. Oops. I cannot wipe out like on a blackboard. I almost can. Right? So what we proved here, and I think that is a much better statement than saying generic J, we proved that there is a subset of compatible almost complex structures we defined them as something called BJs that are regular. So regular is a certain property, namely regularity means that the d-bar operator is transverse. So that's a definition. Now you can check whether a J is in this set or not. If you just say generic, I don't know how to check whether a J is generic or not. So regular J's that's a good word. And as a subset, we proved that this is not only not empty, but in fact comeager. And in this metric space, comeager means it's dense, complete metric space. And that's what people, so once you have a comegal set, one often refers to the points in that set as generic points, because it's sort of almost every point, is in this set. So, and so for those generic points, so for those J's, for the regular J's, we have not only this transversality, but so for all J's in this space, the moduli space of pseudoholomorphic curves with point constraint, right? So going through this point without a compactification, right? Is already compact. There was no bubbling, and that was my index calculation. This is expected to be zero-dimensional, and in fact, it is. So. Not only that, I also argued that if you fix two regular, almost complex structures, then the two moduli spaces are cobordant. In fact, we made a cobordism from another moduli space that used a homotopy of J's. But what's mainly important is that this is a one cobordism. So whose two boundary components are, whose boundary components are the disjoint union of J1 moduli space and the J2 moduli space. I had called them J0 and J1 because J1 was the one that we actually wanted to construct, and J0 was the simple, almost complex structure for which we knew that there was a curve, exactly one curve. The reason this is good is that, so this together, right? So I have a recipe for making smooth manifolds, and the outcome is sort of independent of that recipe, at least up to cobordism. This together is what I would call regularization. In fact, actually, so regularization, I would say, has three components. One is a manifold. The other one is that it's compact. That's the only way I can count it or give it a fundamental cycle. And then the third component is the cobordism. Whereas transversality here is just this little bit here.
Regularization does not mention anything about
orientability. Well, you will want to regularize orientably at some point, otherwise you're really not going to get fundamental classes. The one reason I don't have to worry about orientability here is that for zero manifolds, somehow a fundamental class makes sense with the two coefficients. So the counting mod 2 makes sense. So in some sense, integrating integer homology classes over an unoriented zero manifold makes sense. But I don't know how to integrate anything over an unoriented one manifold. So that's So, and the upshot of this is in fact, so since I haven't talked about orientations, that the number of points in this moduli space if I count mod 2 is well defined. Not only well defined, it's also independent of J. And, well, here, I've worked with a very specific point here, but one can actually also prove that it's independent of the point by a similar cobordism argument. And so this here is your first example of a Gromov-Witten invariant. So that is, I think, honestly and strictly speaking, what I actually did prove last semester. So I ended the semester, at least in terms of notes, with a little bit of a puzzle that asked, did I actually prove Gromov non-squeezing? We wanted to find a curve in this moduli space, but for a somewhat specific J. So here's a condition on that J1. Right? I'm prescribing this on a pretty large open set. So that means all of these J's could lie outside of this dense set of regular J's. So here the puzzle is, on some level, can I push this Sartre theorem enough to actually make sure that I can find a specific J1 that also satisfies this condition? And I think me sort of giving 2 or 3 different arguments and not actually being sure that any one of them really works is a good reason for this course. So this is subtle stuff. However, so we should be worried about my state of mind and regularization in general. We should not be worried about Gromov non-squeezing, because I can pick any one J that satisfies condition A. And then I can take a sequence of regular J's that converge there. And then instead of doing this nice cobordism argument, I can just say, well, now for every of the regular J's, I'm going to have exactly one curve. And so I'm just going to look, I'm going to have at least one curve, because that's what the Gromov-Witten invariant for those is going to tell me. Right? And so then I can run my Gromov compactness argument, and in the limit I'm going to find, well, potentially a bubble tree for the J that I actually wanted. But then again, I'm going to argue bubbling didn't happen. So in the limit, I do actually find a curve. It is just a little more ugly than,
But if I recall correctly, all J are irregular in this situation.
Yes, that would be nice. That requires something other than the Sartre-Smale.
Yeah, you have to.
Right. You have to actually understand, right, the obstruction bubbles. I also actually believe that if you're really, really careful about sort of the PDE arguments, and there's some kind of subtle measure theoretic argument that comes in, you can prove this directly by a Sartre-Smale argument. But I think that's for offline discussions and potentially and after our correction also to those lecture notes. So, that's the reason I feel I have a right to say regularization is hard because I make mistakes. So, right. So that was an example of getting zero manifolds for some j's and having cobordisms. And that's an example of making this rigorous, and how one want to make these things rigorous will be the content of more philosophy, and hopefully eventually at least, well, I'm not going to be able to actually prove any of this. The goal will be to give you the language and the basic ideas to apply these things, and if you feel so inclined, to try and check proofs. So that's the goal.